Okay, so let's take a crack at our first question. Like in the question, suppose a function f has a power series expansion at a point A, element of R. So by definition, this means there are Cn, so this collection of numbers Cn, element of R, and an R greater than 0, such that f of x equals sum n equals 0 to infinity Cn x minus a to the n for all x such that the distance between x and a is less than r. And I'm going to call this equation star. So the first thing I want to do is recall our result from lecture C, which says that as the power series above converges on this open interval, in particular, at each point x, it converges to f of x, but that's not important at the moment. All we need for the moment is that it does converge. We have that it is infinitely differentiable. Infinitely differentiable, as in we can differentiate as many times as we want at a. Okay, so star then tells us that f is infinitely differentiable at a. Okay, so the power series is infinitely differentiable at a, and we have this equality on this open interval between f and the power series, so that then tells us that f is infinitely differentiable at a, and this will be very important as we proceed. Okay, so let's rewrite star in the dot 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 notation. So we have f of x is equal to c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus dot dot dot. Okay, and let's plug x equals a into star. And what do we get? So on the left hand side we get f of a is equal to c0 plus c1 a minus a plus c2 a minus a squared plus c3 a minus a cubed plus dot dot dot. Okay, and now all of these terms after the first term are going to be 0 because a minus a is 0. So the partial sums converge to c0. So we have f of a is equal to c0. So we have solved for c0, i.e. if f has a power series expansion at a, we know what c0 has to be, i.e. c0 is unique. Now, from our remark, we can differentiate both sides of star to get a new equation, which we'll call star 1. And it says f prime x equals 1 times c1 plus 2 c2 x minus a plus 3 c3 x minus a squared, just differentiating term by term on the right, plus dot dot dot. And as above, we're going to plug in x is equal to a. So let's plug x equals a into star 1. And we're left with f prime a is equal to 1 times c1 plus 2 c2 a minus a plus 3 c3 a minus a squared plus dot dot dot. And again, the only thing that survives is the first term. Everything else goes to 0. So we're left with 1 times C1. And I'm leaving the 1 here for a reason which will become clear shortly. Okay, so like C0, we have now solved for C1, so it is also unique. So let's repeat the process and differentiate star 1 to get a new equation, which we'll creatively call star 2. And it says f double prime x is equal to 2 times 1 times C2 plus 3 times 2 times C3 x minus a plus 4 times 3 times C4 times x minus a squared. Again, I'm leaving the coefficients like this for a reason. And again, we're going to plug in x equals a. And what do we get? F double prime a equals 2 times 1 times C2 plus 3 times 2 times C3, a minus a, plus 4 times 3 times C4 times a minus a squared, plus dot dot dot. And again, the only term that survives is the first term. Now, why have I written it as 2 times 1? Well, I want to write that as 2 factorial times C2. Bringing the 2 factorial to the left-hand side, we can now write C2 is equal to f double prime a over 2 factorial. So again, we have solved for C2, so it is also unique. So it's a good point in the video now to pause and try and repeat these steps to solve for C3 and C4, and then try and see if you can see a pattern. Okay, so hopefully you got C3 is equal to f triple prime a over 3 factorial, and C4 is equal to f differentiated 4 times evaluated a over 4 factorial. And you've seen the pattern, which is Cn is equal to f differentiated n times evaluated a over n factorial. Okay, so that's the general formula for Cn. So to summarize the significance of this, we will have the following remark. So remark, we have shown that if f has a power series expansion, at a point, a element of R, then it is unique. Okay, so if f has a power series expansion at a point, it is unique. This is stated more explicitly as a theorem in your lecture notes on page 5, so I'd advise you to look at that. Okay, so with this remark in mind, we're going to make the following definition. If f is a function with infinitely many derivatives at a point A, then the Taylor series of f at A is the power series Tx, so we're going to represent this by Tx, and it's defined to be the sum from 0 to infinity f differentiated n times at A over n factorial x minus a to the n, which in the dot 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 notation is f evaluated a plus f differentiated once over 1 factorial times x minus a plus f differentiated twice evaluated a over 2 factorial times x minus a squared plus dot dot dot. Okay? So if A is equal to 0, this series is known as the Maclaurin series. So Maclaurin series is just a special case of Taylor series. So the Maclaurin series of f, which is sum n equals 0 to infinity, f differentiated n times, evaluated at 0 instead of a, over n factorial, and then just x to the n. And in the dot 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 notation, that's f evaluated at 0 plus f differentiated once evaluated at 0 over 1 factorial times x plus f differentiated twice evaluated at 0 over 2 factorial x squared plus dot dot dot. Okay, so this is the Taylor series and the Maclaurin series of f. And again, if you read the first line of the definition, it's very important that f has infinitely many derivatives at a. Otherwise, this makes no sense, because if you look at the definition of tx, we have f differentiated n times, and n goes on to infinity. Okay? So the infinite amount of derivatives is very important. An important point in B is to say that in the previous definition, we are not assuming that f has a power series expansion at a. We are only assuming that it has infinitely many derivatives at a, which is a different idea. Okay, so this can be quite confusing at first, as there are a few subtle but very important points at play. So what I'm going to do now is try and encompass these into 2 remarks. So remarks 1. If f has infinitely many derivatives at a point A, we can construct its Taylor series at A, which we called Tx. But in this situation, we have no information about when f of x actually equals Tx. Other than at A, we don't know when these two things are equal. Second remark, if f does in fact have a power series expansion at A, so it's a big if, but if f has a power series expansion at A, say on the interval a minus r to a plus r for some positive number r, then we must have f of x equals t of x equals sum from 0 to infinity f differentiated n times evaluated a over n factorial times x minus a to the n on this open interval. And this is due to the work we did answering our fundamental question 1. So, i.e., just to rephrase this, if f has a power series expansion at a point A, that expansion must be its Taylor series at A. Okay, so the subtlety is this. Having infinitely many derivatives allows us to construct Tx, but it gives us no guarantee that f of x will equal t of x on some open interval. In fact, at the end of the lecture, we will see an example where we can construct Tx, but there is actually no open interval where it will agree with f.